And this problem can be done with negative values, but we don't want that. That's too much work. And so what we want to do here is that we want to go in and we want to interpret this where we know that the only thing that matters is energy differences. That's all we care about. It says, let's read the question. It says, a conservative force acts on a 2 kilogram particle, right? So we know that the mass of the particle is 2 kilograms. And it says the potential energy function is graphed. When the particle is at x equal to 2 meters, its velocity is negative 1.5 meters per second. What are the magnitude and direction at this point? Okay, so what do I know here? Well, look at the numbers. They're sort of like all screwed up for us, right? Look at that. I have negative numbers. Ignore the negative numbers and make this problem your problem. So if you were to look at a problem like this in a textbook, they would want you to use this scale. That's BS. Remember, you control where potential energy is equal to 0. So guess where I'm going to pick my 0 point? I'm going to come in here and I'm going to just say this. I want my 0 point right here at the bottom. Okay? So I'm going to do this. If I set this right, I'm going to say right here is where I'm going to set my potential energy equal to 0. Okay? I want to know, and that value, look at that value, you could see here is that they will tell you that choose negative 17. So in other words, the book implies you have to use negative 17 joules for that value. And you know what we're going to do? Carlos says that's bullshit. I'm going to use 0 joules. Why? Only energy differences are meaningful. Okay? So let's get a view of this thing. It says that the particle is starting at 0.2. Okay? 0.2. So where's 0.2? Here's 0.2 right here. So that means it's got to be where? It's going to be right there. So what I need to do here is I need a color that's going to really stand out. I think I'm going to change this to a lime green to see if I can get that to stand up. That means the particle is standing right here. So let's count. Let's do a counting. So if I do a counting of this thing here, that means look at my 0 potential. What is the potential energy of this function? Relative to our 0 point, I got to count. So look at this. That's at 7. This is at 17. So look what I'm going to do. I'm going to come in here and I'm going to just say at this point, all I'm doing is that I'm counting squares. I'm going to call that U of 2. In other words, that's how much potential energy it has relative to my 0 point. So note I'm going from negative 17 to 7, but what I'm going to call that is I'm going to call that what? I'm going to come in here and I'm going to say define potential energy equal to 0 at the location that we're going to look at at the negative 17 joule mark. That's my zero potential mark. So what I'm going to do here is that now, look what it says. It says it has a velocity of what? 1.5 meters per second, right? It has a velocity at that, but kinetic energy doesn't know the difference. So then at point x equals to 2, we read off the graph that at this point, which I'm going to call 2, it has 10 joules. Now, and it has a speed of minus 1.5 meters per second. But we don't want speed, we want energy. So then what we're going to do here is that let's determine kinetic energy. So if I look at the kinetic energy, it should be at 2, it should be 1/2 m v squared of 2. And if I compute that, it should be 1/2 times 2. What's the speed again? 1.5. Remember, it's 1.5 squared, so that's a positive number. So you get 2.3 joules. Let's put in the kinetic energy. So then that means here that when I draw in my kinetic energy, look what happens. Well, how do I get 2.3? I'm just actually going to put 2. That's my kinetic energy at 2. So now that I have all of that energy, what's my total energy line? Look at my total energy line. It's going to do what? It's going to go right across this line right here. And I'm going to draw, let's say, what am I going to draw? I'm going to draw a green line. This is my total energy. What's my total energy? It's going to be 10 plus 2.3, so it's going to be 12.3 joules. So now, if I look at this picture, what do you think is going to happen? So if I look at this picture, you could see that if I have my green object right here, right? There's my green object. What happens when the object is right here? Right? What happens when the object is right there? You can see that it took all that potential energy and it converted into kinetic energy. So let's write that point here. So what I'm going to do here, let's make this point that 5. Why 5? Just because it's easy. So if I look at point 5, look what I'm going to do. I'm going to go just right off of this thing, and you could see that when I get to right here, this is now all been converted into kinetic energy. And then if I continue to go up to the ramp or something, you could see here is that the maximum height that this thing will ever get to is when it's converted all of its kinetic energy into potential energy. And look at this point right here. When it gets to right here, this point, it looks like it's 14 meters. At 14 meters, you could see that that's the maximum total amount of energy that it could ever have. So if I go over here, so check that out. I can see here is that at this point, that this is the potential energy at 14, and the maximum potential energy that it will have will be 12.3 joules, and the maximum kinetic energy that it could have would be 12.3 joules. So look what happens. So if I was to take this picture now, and now that we have conservation of energy here, look what I'm seeing here. So now, the overall picture of its motion is like this here. It's going to look like that. So what's going to happen to the ball? Well, you could see here is that from what we said up here, the maximum height occurs at that -5, right? So 14 is the maximum height right here. So our energy picture determines what that maximum height is here. So this line is our line of maximum height here. So what happens here is that a particle can do what? If it's released from this spot right here, then what's it going to do? Well, it's going to move in this direction. And as it gets down here to the bottom, we could see that it's got to be moving the fastest right here, right? This has to be maximum speed. And then it's going to come all the way up to the top. And where's it going to stop? Right here. We know that at this point here, the speed is 0. We know that the speed here is 1.5 meters per second. And so what happens when it reaches the top? Well, it ran out of energy. So what's it going to do? It's then going to reverse the process. That's how you use potential energy functions. This is our energy barrier. A particle can never be in the forbidden region. So now all I have to do here is that I can go answer the question, but look how intuitive potential energy functions are. It's like if you were riding your bike and you saw a dip like this, you'd know exactly what would happen. If you write down the potential energy function, you know exactly what that particle is going to do. So let's go and do the calculation so that you could see that it makes sense. So that way we don't have to think about this. So here we go. So now let's see what the question says. If I could just find my mouse. It says here we go. What is the magnitude direction of the force at this position? So in other words, the question is this, right? So if I look at A, what is magnitude and direction of F at x equal to 2 meters? Well, we know that F has to be what? We know that F has to be the negative slope of the potential function. So it's got to be negative of the slope. So right away, we could see here is that the slope at x equals to 2 meters is clearly negative. Therefore, the force at x equals to 2 must be positive. So to get its magnitude, we need to get the slope value. So then, if I look at the slope value, I got to go calculate delta u, delta x. Well, I just got to pick 2 points. So let's say that this point right here, let's pick this point right here. Let's see. Let's pick this point right here. Let's call this point, I don't know, that's point at 4. So I'm going to get the slope from this guy's going to be 4. So if I look at this, this is going to be 4. And the value here is going to be negative 17. And then I'm going to pick another value, which I think is nice. How about if I pick this point right here? That point right there looks like it's 1, and it's 1, 2, 3, negative 3. So there's my slope values. So what I'm seeing here is this, that at x equal to 1, I have minus 3 joules. And at x equal to 4, I have minus 17 joules. So what's my slope here? So my slope should be, I can calculate the magnitude of the slope. That's all I care about. We already know that the slope is negative. So it's really, I'm going to pick 17 minus 3, right? So I'm going to get 17 minus 3 divided by 4 minus 1. And so that's going to be 14 divided by 3. And that slope value, I don't know what that slope value is. It's going to be almost 5. So I'll approximate this and just say that's pretty close. So I'll say 4.9 Newton. Well, it's going to be 4.9 joules per meter, which is 4.9 newtons. And so if I now combine these two, we then see that our force is then going to be what? It's going to have a magnitude of 4.9 newtons, and it's going to, and its direction is equal in the positive x direction. It's in the positive x. And that's what the force is right there. No surprise, because we knew that the ball would have a force in the opposite direction of the incline here. Okay, so if I go to the next piece here, it then says, we got A, we got that. So then it says C, left and right. Between what positions will the particles go? Well, we actually already answered that question. So if I look at B, B is, maybe I should just bring that down because that's, let me do this down here. So if I look at B here, I could then come in here and go, we're looking at C. So it says, between what positions will the particle on the left and right? So we already said that this was the maximum right here because that was the total energy mark. So I'm going to guess here that this looks to me like this guy is going to be what? 14 meters. And I'm going to say that this is in between. So if that's 1, I'm going to guess that this distance here is going to be 1.5 meters. What determined that was our total energy line, right? This is the line where the total energy was a constant. That's what determines that. So if I look at C here, so then that means that the range of motion is between 1.5 meters and 14 meters. So in other words, for this energy, the possible ranges of motion is this guy right here. And we used our energy picture. So then it asked the last question, E here, it says, what is the particle speed at 7? No, we almost answered that because when you come back up here, look what we said here. We said that the maximum kinetic energy would be right down here at the bottom. And so since we know what the kinetic energy at 5 is, note at 7, it's exactly the same thing. So I know the kinetic energy is 12.3 joules. So therefore, we could say the following thing. So if I look at E, what is the kinetic energy at x equal to 7 meters? Well, we saw that the kinetic energy at 5 has to be the same as the kinetic energy of this, and we saw that this was 12.3 joules. But kinetic energy is then going to be 1/2 mv7 squared. So then I could go in and I can solve for 7. So if I look at this thing here, what am I seeing here? Well, this guy tells me that it's got to be V7 has to be 2 times K7 divided by the mass square rooted. So if I look at this value, it's got to be 2 times 12.3 meters per second squared. Did I say 12.3? Joules. should be joules, divided by the mass, which is 2 kilograms, and then I got to take the square root. And if my calculator is right, I get a value of 3.5 meters per second. And that's what the speed is at 7, as well as 5. So if you can write down the potential function of your system, man, is it a powerful way of doing this thing.